Hi guys, welcome to an SD WAN video. In this video we'll have a look at Cisco SD WAN components in particular and their roles within the software defined WAN fabric. So before we dive into SD WAN, let's quickly go over the problem and why SD WAN is required. So users here on the left hand side, whether it's a co-location, branch office, head office or any other type of office, have routed all their traffic to the data center, whether that is to access services located within the data center or services such as the internet via the data center. So this has been a great architecture for years, as each office didn't need their own connection out to the internet, and all security controls such as enforcement and monitoring was done through the data center, and the data center was the single point of entry for all this traffic, which made it manageable and cost effective. So typically we have used a WAN and most likely a backup WAN to connect to the data center and a backup data center as well as the internet and other offices and sites, and this comes with all the complexities of routing and the different transport types we use to provide connectivity to the WANs, such as fiber connectivity or 5G, Metro Ethernet, MPLS, VPNs, and there's lots of others as well. So looking at the next slide, the traditional WAN and the growth of services today. So as the years have gone by, we have got the same hub and spoke topology where all users are going through the data center, but with the additional services on the right hand side being introduced, such as cloud and SaaS based services such as Office 365, Salesforce, OneDrive and many others. And there are other cloud based services as well as other requirements such as connecting into third-party organizations. We can see a site-to-site VPN connection going into a third-party organization here, as well as a Microsoft Express route to Microsoft Azure, and there may be other connectivity requirements as well. And with all of this, or at least most of it, backhaul through the data center in a hub and spoke like topology, which clearly means the DC has become a massive bottleneck and it's no longer the most optimal and efficient way of accessing services. So if we draw the additional data center here to show how complex it can be, if we draw a data center and draw the connectivity to the offices, we can see very quickly how complex it can become. And the last one to the third-party organization. So basically, by drawing all of these connectivity links using a backup data center, we can see it's become quite complex really quickly. And with applications and services that are accessible directly using the internet, why would we want to be going through the DC to access everything? It's clear to see internet bandwidth at the data center has become a huge bottleneck. Connectivity and routing has become more complex with things like active data centers, secondary backup links and so on. And it wasn't an issue as much before when there were no cloud based services or much in the way of remote networking. Before there were options available, but it came with their own challenges. For example, although we could break out directly out of the branch offices to the cloud services, we would have to consider security, as there is no security in the branch offices, which was a clear issue. All the security solutions were in the data center or hub office, and we would have to consider local management of the devices within the remote offices as well. Another area to consider is the limitation around MPLS, where providers can take months to provision a new MPLS line. One of the big challenges to MPLS has always been the time it takes to deploy a network. And with remote users working from home, which has gone through the roof with COVID lately, from home with home tunneling, all traffic through the VPN in the DCs is another area for significant impact on performance. For example, remote users accessing Office 365 and OneDrive through the VPN tunnel is one of the major examples of where performance has been heavily impacted. So it's time for vendors to start looking at something different that was just as reliable and quick as MPLS, but where we can eliminate expensive lines such as MPLS and still provide the high reliability of what MPLS has brought to the table, but with a combined use of other cost-effective transport links such as the internet, 4G, 5G, radio, satellite, Wi-Fi and so on. this leads us to the next slide, which is the introduction of Software Defined WAN. So this is where SD WAN comes into the equation, and with SD WAN, with the use of SD WAN, users can have direct access to everything. Everything is a single hop away. Every office, site, co-location, etc. can access everything else, directly bringing users closer to the applications, closer to multi-cloud, SaaS-based applications. The general internet, data centers are all now accessible, and all traffic is no longer backhauled through the data center. They're all accessible directly. So you can see in this diagram on the right hand side where the users are accessing services using any of the traffic mediums and have direct access to all of the services, as opposed to going through a data center architecture. And this is all done with software defined architecture, which includes devices within data plane, management plane and orchestration plane, which we will cover off in the next slides. And with the use of SD WAN, policies are used closer to the user to determine where to go to access applications, which links to use based on their current state, and lots of other controls. And this capability comes into play due to the use of SD WAN Edge devices that are placed in each office and managed by a central controller that is able to manage the whole SD WAN fabric from one central location. And we will cover the Cisco version of SD WAN and its components in the next slide. MPLS connectivity is expensive, and therefore with SD WAN, offices can use other connection types such as the internet or even a 5G connection as a second backup line. You can even set different policies, such as policies based on application. You can choose which link to use. So there's no more reliance on the traditional stuff such as MPLS, DMVPN, IWAN, and many of the connection types are listed here within the diagram in the middle. So in the middle you can see cable modem, ADSL, Ethernet, etc. that are all available to use as traffic mediums in SD WAN architecture. And there's better visibility and availability provided with SD WAN, as it's a software defined architecture separating the control plane and the data plane, with a controller that is able to view and control everything. SD WAN components. So let's have a look at the SD WAN components, which makes all of this happen. SD WAN is broken into 4 main components which sit within the 3 different planes, which are the WAN Edge routers, which are part of the data plane and does all of the forwarding of the traffic between the sites. vBond, which sits within the orchestration plane. vSmart, which sits within the control plane, and vManage, which sits within the management plane. So quick overview of what's going on here. So on the left, these are our edge routers located at each branch office. They first talk to the orchestration layer vBond devices to initially set themselves up into the SD WAN fabric. The vBond sends the router config and tells the router where the vManage and vController devices are located. From there on, changes are made via the vManage devices and everything is controlled via the vSmart controllers. As the control plane has been separated from the data plane, the controllers can now see the whole network and control all of the routing information, and has a bird's eye view of all of this. The control plane can see all the routers and what they are connected to, where the edge devices have set up VPN tunnels and so on. So this is the magic with SD WAN, where the control plane is separated from the data plane and can see everything. So now the devices can access cloud services and internet directly without having to go through the DC, because the policies are sent to them via the controller. They have policies set on them and they will be told which links to use to get to the cloud services, which links to use to get to the internet, what security policies to use to enforce on those devices to keep them fully secure, rather than going through the data center to apply the same policies in a traditional hub and spoke network. And this is what makes SD WAN so much more efficient and scalable. So the first component we will discuss is the WAN Edge devices. The WAN Edge devices sit at the edge of a local office and does all of the forwarding of the packets and the enforcement of policies for all of the clients within the edge offices. WAN Edge initially takes part in what is called zero touch provisioning, basically onboarding process, provisioning and adding themselves to the WAN fabric. This includes authentication, provisioning, any NATing with vBond, and vBond then provides the details of the vSmart controllers and vManage devices to the WAN Edge devices, and this is how connectivity is established between the WAN Edge devices, vManage and vSmart controllers. The Edge devices establish a connection with vSmart controllers using a dynamic routing protocol known as Overlay Management Protocol. This is the routing protocol that runs inside the overlay and is used for control plane information between the smart controllers and between the Edge devices and smart controllers. The Edge devices also take part in the normal routing protocols as well, such as OSPF, EIGRP and BGP, and creates IPsec tunnels between sites for sharing of resources over the tunnels. You can see this as the data plane traffic. With IPsec VPN tunnels, you can configure them using different topologies such as full mesh, partial mesh, hub and spoke over each of the connected mediums, and bidirectional forwarding detection protocol is used by default and runs over each of these tunnels, and this is to be able to detect loss, latency, jitter and path failures. The next component we will discuss is the vSmart controllers. vSmart controllers sit within the control plane, and its main role is distributing policies to the WAN Edge devices. You can distribute policies to the Edge devices such as application security and QoS policies, and vSmart informs all of the Edge routers where the other devices are and pushes VPN configuration to the Edge devices. Just to make a note, vSmart sets the tunnels up via the control plane channel, which is a secure communication channel using DTLS, and the data plane is secured by the IPsec tunnels that are established between the WAN Edge devices. So if a controller goes down, the data path still works as the control plane information such as routing has been stored locally on the WAN Edge devices. vSmart manages the routing decisions for Edge devices using the Overlay Management Protocol for management of routes, and vSmart sends all of the control plane information needed to build tunnels between the Edge routers using the Overlay Management Protocol. So when the control plane discovers all routes, these are shared with all the Edge routers or reflecting them back to the Edge devices, which is similar to a route reflector in the BGP world. Any route manipulation or filtering is done here as well. To differentiate the vSmart controller from vManage, vManage is the GUI which configures the fabric, which we will get onto in the next few slides, where vSmart controller controls the fabric, such as control of the routing information. The Edge devices know where each other are via the control plane. vSmart uses OMP for this, and the Edge devices peer with the vSmart controller for control plane information and do not peer directly with each other, and this is where the magic lies in Software Defined WAN or Software Defined Anything, by separating the control plane and providing a single place of management control and a view of the entire fabric. So vSmart can be deployed in the Cisco cloud, which is really AWS or Azure cloud, in a private cloud, in a managed service provider environment such as a managed service, or a private data center within the customer's own data center, which is usually done when the customer is mandated by its own security requirements. vSmart and actually vBond as well are typically set up in the cloud in multiple regions in active state, and in the case if there is a fault at any region, then all traffic will fail over to the region that's up. So very resilient setup. And finally, on vSmart at this moment in time, if I'm not mistaken, vSmart is a virtual only appliance. The next component, vBond Orchestrator. Looking at vBond, which sits in the orchestration layer, works like a bootstrapper and is the first point of contact for Edge devices. The Edge devices get the config from vBond, and vBond facilitates things like NAT traversal, and it has a multi-tenant or single tenant capability, and ideally needs to sit on a public IP address. So it's the first point of contact, and the main role of vBond is for the Edge devices to get the config from vBond. Only devices authenticated by the vBond will be permitted to talk to the vSmart and vManage, and this is all done using serial numbers and certificates. It's all certificate based authentication, and you can use a private or public key infrastructure for this. With vBond being a virtual out-of-band device responsible for onboarding devices into the SD WAN fabric, therefore new WAN devices speak to vBond first, and then vBond provides that information to vManage. And one of the ultimate goals for vBond is it is responsible for zero touch provisioning, controls management information, controls NAT, amongst other things. vBond orchestrates the connectivity between the edge routers and vSmart controllers. It also ensures that valid edge routers can build the control plane connectivity, and when the edge devices come online, they ask the orchestrator where the smart devices are, in which the vBond orchestrator gives them that piece of information. And vBond, like the vSmart, is a virtual only appliance that needs to have a public IP address to be contactable and can be scaled up to 6 devices. The next component is vManage. So with vManage, it is basically the graphical user interface, which is able to manage all of the SD WAN components and is used for onboarding, management activities such as policies and troubleshooting, upgrades, configuration of templates, and basically day 0, day 1 and day 2 operations. It's basically the management of the fabric, how you manage everything and anything within the fabric with a management GUI. vManage can be programmed through a RESTful API and netconf as well. It's basically the management of the fabric, just like how you would manage anything else within the GUI. So netconf is used for various tasks such as communication with SD WAN devices. vManage uses netconf to retrieve information from other management components when they are added to the vManage. And the Cisco SD WAN vManage API is a REST API for controlling, configuring and monitoring the Cisco devices in a overlay network. Some of the use cases for vManage API are to monitor devices, configure devices, such as attaching a template to a device, querying and aggregating device stats. vManage is an out-of-band appliance, so if it had a failure it wouldn't affect the network. Only it would affect the ability to make changes while it's out of service, so typically deployed in an active standby state. Cisco vManage offers 3 dashboards, which are the main dashboard, which provides information such as the status and health of the network. It provides a security dashboard, which provides the status of the security features enabled in the network, and a VPN dashboard, which provides information about the VPN segments in the network. And finally, vManage supports up to 2000 devices per instance, and you can scale it up to 6 vManage devices. In the last slide we will cover some additional features and terminology which is key to SD-WAN, and the first one is policies. So you can configure policies on the edge devices such as path selection and application policies using 6-tuple lookup with a license and the use of deep packet inspection, which is basically using a database of lots of applications, and then we can send certain applications down one link and other applications down another link, for example. So prime example would be sending VoIP traffic down a more reliable and faster link, where using the less reliable link to browse the web. Other policies such as QoS and security policies can also be implemented. In the SD-WAN overlay, VPNs are used for traffic segmentation, like VRFs that are used on switches, and VPNs can be used to provide multi-tenancy in a service provider environment, or to split off different sections of a company when used by an end user, possibly for security requirements for highly sensitive companies. There are two main VPNs that exist by default in the WAN Edge device and controller, which are VPN 0 and VPN 512. VPN 0 is the transport VPN. It contains the interfaces that connect to the WAN transport links, and the other one, the VPN 512, is always used for out-of-band management for connectivity between the vManage and the edge routers. Also, the VPNs, known as server-side VPNs, need to be created that contain interfaces connected to the local site network which carries user data traffic. Cloud on Ramp. Cloud on Ramp in the use case of IaaS provides virtual edge routers in the cloud such as Amazon and Azure Cloud to provide connectivity just as you would when deploying an edge router within a branch office. So it's for VMs that are deployed in the cloud environment. The edge routers in the cloud connected to the VMs build a VPN tunnel back to the SD WAN infrastructure using MPLS or the internet as the transport medium. With Cisco SD WAN, you have a feature known as Zero Touch Provisioning, which allows you to pre-configure a device, and when a device is plugged into a network, it picks up its config from the vSmart controller and starts to do with what it was configured to do. So you can ship the WAN device directly to the office and ask someone to plug it straight in, and without any further configuration the device finds the vBond server and pulls in the config and it's up and running. The Zero Touch feature is also part of the Cisco DNA Center I've covered in a previous video. The last bit of terminology we'll look at is TLOC, which stands for Transport Locator. TLOC is used to tag the different pathways an application can take, so you can manage the different types of connectivity methods with the use of tagging each transport link to the outside world you would use for the different applications. For example, you would tag internet with a coloured tag of blue and MPLS with a coloured tag of green, and then you can configure a policy to send out Office 365 traffic over the blue link and connect to the data center specific apps on the green link. And this can save time for where, for example, if there are 500 branch WAN Edge devices which use different interfaces for the internet link, where some are connected to Ethernet 1, some are connected to, let's say, Ethernet 3 and others to other Ethernet interfaces, it makes it very difficult to apply policies to because they're all connected to different interfaces. However, if you tag the internet link regardless of the physical interface it is connected to with the colour of blue, then you can use the colour blue to apply policies to, and this is where tagging by colour proves to be very handy and a time-saving feature. And that's it for this video on SD WAN. Thank you for watching.